For 22.2 reassessment, I chose some examples from the book. For my first problem, there is a uniform tangent magnetic field in the circular path. If the radius is 3 centimeters and the magnetic field along the path is 1.3 times 10 to the negative 6 Tesla, what are the magnitude and direction of the current enclosed by the path? First, I determine the value of B and dl in Ampere's law. I use the product of B dot dl to find mu naught times the sum of the conventional current inside. In order to find the amount of current, I needed to divide this answer by mu naught. To determine the direction of the conventional current, I used the right-hand rule, where my fingers were in the direction of the magnetic field, which meant that I was 0.195 amperes into the plane of the circular path. My next problem was very similar to the previous. I worked this problem in sections, with my path starting at the top right-hand corner and continuing counterclockwise around the rectangle. Because the magnetic field on the top and bottom are not in the same direction nor perpendicular to dl, there is only a small contribution of the magnetic field included in the total from both these sides. And because I chose my path to be counterclockwise, the contributions of these sides are both negative, which simply means that the magnetic field is opposite dl. Because the magnetic field on both the right and left side are perpendicular to dl, they have no contribution to the total outcome of the value of Ampere's law. For this example, I found that the sum of the current inside times mu naught equaled 1.57 times 10 to the negative 4 Tesla times meter. For my summary of Ampere's law in this reassessment, I chose to show the relationship of a situation where there are two long solenoids, which are nested on the same axis. Both have the same conventional current, but in opposite directions. The inner solenoid has the radius R1 and N1 number of turns. The outer solenoid has the radius R2 and N2 number of turns. For this first region, R is greater than 0, but less than R1. First, I found the sum of the conventional current inside, which equals the number of turns of solenoid 1 times the length times the current plus the number of turns of solenoid 2 times the length times the current. Since I is equal in magnitude but opposite in direction, the component of one of these solenoids must be negative. By moving around this path, I was able to find the contribution of each side. The contribution of the top and the bottom are 0 because B is perpendicular to dl. Therefore, B dot dl equals 0. The right side of this path equals 0 because there is no magnetic field on that side, which means that the closed interval of B dot dl equals just BL. But really, BL actually equals mu naught times the sign of the current inside, which I have already determined this component to equal this value. Therefore, I can solve for the magnitude of the magnetic field to get this equation for this region. For this region, where R is greater than R1 but less than R2, I work to find the magnitude of the magnetic field the same way. All aspects were the same as before except for the sum of the conventional current inside. For this region, the total conventional current inside equals the number of turns of solenoid 2 times the length times the conventional current, which means that the magnitude of the magnetic field would be simplified to look like this. For a region where R is greater than R2, I know that the magnetic field would be 0 because the net current enclosed by the loop is 0.